Thank you, Vanessa. Good morning, good afternoon, good evening to everybody attending this webinar, and thank you for your time. Just to give you a little overview of the deep dive series that we've been doing with topics pertaining to additive manufacturing. So the first one happened on the 3rd of July, which was predicting additive manufacturing build cracks using XFIM, basically combining the technologies of additive manufacturing and Abacus, and kind of like coming up with a holistic solution to predict the cracks in different parts. Today's topic, which I will be going over, is the lattice optimization and process simulation of a turbine blade. And we have 4 more eSeminars on our way, and they've been slated tentatively at these dates, and closer to these dates you will probably get an update if the dates have changed or if it's going to be on the same date. So to give you a little more background on our solution for additive manufacturing, Dassault System solution on additive manufacturing, for more information I would highly recommend you to use the QR code or the website link that is there right below the QR code to go and find out about our solution, how we basically take a part from starting, meaning from conception all the way to production. And there are how-to videos, there are technical papers, validation references, customer references, events and webinar recordings that are available for you in this website. So all you need to do is sign up, and then you will be able to watch all the webinar recordings, and then you will also have access to all of this great content that's there on this website. So here I'm playing a small video, which is a teaser.
Hello, and welcome to the instructional series. If you are a complete beginner on a 3D experience platform and want to perform simulations of an additive manufacturing process, you have come to the right place. This manual is a comprehensive introduction to defining and conducting additive manufacturing process simulations. Step by step, you will learn how the 3D Experience platform delivers a highly accurate end-to-end solution for digital additive manufacturing, which spans all the way from functional generative design through manufacturing planning and process simulation to final shape compensation. In this manual, you will gain a basic understanding of the 3D Experience interface, such as navigating the 3D Experience platform, creating and importing geometries, and assigning materials. Understanding these topics will be a great start for you in learning how to set up the virtual additive manufacturing process. In this series of videos, you will see how the functional generative design application is capable of optimizing and refining the concept shapes of an assembly, validating them, and performing geometry reconstruction for additive manufacturing. You will also learn how to define the build layout and prepare the part for additive manufacturing. In addition, you will learn how to design and optimize support structures. Furthermore, you will discover how to generate and visualize the slicing and scanning path for the build layout. Using the additive manufacturing process simulation application, you can simulate the printing process, allowing you to study the temperature profile, history, and overall build distortions and stresses in the part. When the build simulation is complete, we then use the reverse shape optimizer application to digitally morph the original part design to compensate for distortions during the manufacturing process. When we build this compensated geometry, the as manufactured part is equivalent to the as designed part. Thanks for watching.
All right, that was a quick trailer and a teaser as to what is basically coming in our instructional series that talks about how to do additive manufacturing operations, and also kind of like gives you a basic tutorial on how you can learn the platform and how you can navigate and do basic operations regarding geometry creation and material application and so on and so forth. This kind of ties in with the same fact that I mentioned before about digital thread, where you kind of take apart from conception and go all the way to production. And I would highly recommend you to follow the series as and when the content is available. Now, on a very similar note, so we've been doing this for the last, at least we've been having training for additive manufacturing on the for this particular for our solution for about 3 years or so, and 3.5 years actually. And all the training that's available is on companion.3ds.com. So basically, you can, the essentials that you can kind of learn is to how you can navigate the platform, get to know the platform a little more. What are its capabilities, what are its advantages, and the important points associated with it. Then followed by, you can take a course on functional generative design. This will go over topology optimization and lightweighting for additive manufacturing. Then you come and talk about Delmia process planning. So here is where you can take a course on the powder bed manufacturing, powder bed fabrication application, which will guide you from how you can bring the part inside and actually plan your build, followed by process simulation, where you kind of talk about how you can set up your virtual simulations or virtual process simulations to predict residual stresses and distortions. And finally, a course on shape composition, which will allow you to go ahead and digitally morph your geometry based on the displacements obtained in the simulation. So all of this great content is available on companion.3ds.com, and I highly recommend you to sign up if you haven't already, and go through this content at your own pace. Okay, now let's get to the subject matter, which is why you guys are all here. Why are we doing lattice optimization specifically? So in the case of a turbine blade, it's a standard industry design which has been vetted and validated, like industrial-wise at least. So these turbine blades obviously have a certain airfoil design to it, an aero profile, and you really don't want to mess up with the performance of it. But on the other hand, you want to also lightweight it, because anything lightweight in your assembly is always going to be very beneficial in terms of efficiency and cost and whatnot. So you want to lightweight it without changing the design. So the only way to kind of do it, at least one of the many ways, one of the ways that I could think of is to create an internal lattice for this turbine blade structure and optimize the beam radii of this lattice network inside based on in-service loads, which will help in redistributing the weight and also, with the objective to maximize the stiffness of the structure. So this turbine blade has 3 components. It has the top shroud, it has the blade, and the dovetail region. For this particular workflow, I will be focusing on replacing the internal cavity of the blade section only, and replacing it with lattices, and then redistributing the mass to maximize stiffness. So the workflow, this is the overall workflow of how, or rather how the activities were performed. So first, the lattice was generated for the blade. Then the model and simulation setup was performed, where the lattices were represented as beam elements, and it was assembled and tied with the rest of the model, and in-service loads were applied, like pressure loads and centrifugal loads were applied, which then you take the entire simulation and then run it through an optimizer for redistributing weight and also changing the beam radii. Once it's done, you will get the optimized lattice geometry, which can be later re-imported and integrated with the existing lattice that was previously created. You take this optimized lattice turbine blade geometry, position it on the build plate, get some supports, plan your build, and then perform virtual printing of it. So this is the overall workflow, and this is what you will be seeing in this presentation. So the first component is lattice generation. So as I mentioned before, we're only doing it for the blade section of the turbine blade. So we're creating an internal cavity for the blade section, and this is a cross section of how it looks like on the inside. As you can see, there's a cavity. Then a predefined unit cell pattern was chosen. In this case, a star pattern was chosen with the beam length of 4 millimeters and a radius of 400 microns. So once this is done, we get a uniform lattice which is irrespective of what your in-service loads are going to be. So it's just a uniform lattice. It doesn't have any variable diameters yet. So upon creating this lattice, automatically an Abacus input file is also generated that contains the beam mesh in terms of representing it in terms of finite elements. It's automatically generated as well. So you want to take this beam, so the beam mesh already stays in the same location as where the lattice is, so there's nothing, no more operations are required to kind of move it around and position it and whatnot. So the model setup, basically the turbine mesh, so we have the internal cavity which is replaced with lattice beam elements, then the remaining model is still there, which is as a solid. The remainder of the model is meshed with linear tetrahedral elements. Again, this is no specific reason other than just to make the analysis done faster. And we have a total number of elements of 342,000, 354,000 total number of elements, 342,000 being tetrahedrons, and then we have about the remaining as your beam elements. And then this is how a cross-section will look like inside, with your beam elements positioned exactly where the cavity is, and the remainder of the model is all tetrahedron elements, and a tie constraint is created between the two meshes so that the properties are easily transmitted, the loads are transmitted, and there are no disconnected regions in your model. So the simulation setup is fairly simple. Again, it was not to an extent where I did multiple load cases, but it was just a couple of load cases. A static simulation was performed. Assuming that we have compressed gas or high pressure fluid impacting the blade from the leading edge to the trailing edge, I applied a uniform pressure from the leading edge to the trailing edge, and I also included a centrifugal force due to rotation. Assuming that the turbine blade is constantly going to be rotating, I applied a centrifugal force as my loading condition. So these are very simple loading conditions that a turbine blade will go through. Nothing more complicated was introduced into the system. And obviously to prevent rigid body motions, I had to fix the turbine blade at the dovetail region so that we can get some tangible values for stresses and distortions. Okay, so simulation results based on this model. So this is obviously a precursor to the optimization, so I have to create this model by default. As you can see, we have some stresses, and it looks like there are some higher stresses at the region of interface between the blade and the dovetail, which is expected because we're fixing the dovetail, pressure has been applied to the leading and trailing edges, so you will have some reaction forces being developed there, which makes complete sense. And also, just to ensure that the model is completely connected and there are no disconnected regions, meaning if the tie constraints actually work, I had increased the deformation scale factor to 250, as you can see on the screen, to invoke some exaggerated deformations just to see if I can see any beam elements flying around or if I can see any anomalies in the model. And in this case, I did not see any, which kind of ensured that the model was completely connected and the loads were transmitted throughout the internal structure of the turbine blade. Okay, so this, as I mentioned, is a precursor to the optimization workflow. So let's see how we set up the optimization workflow. The optimization workflow was also done on the platform, on the 3D Experience platform, basically as an activity, as a sequence of events that was automated. So we created a utility which would export an input file, like an Abacus input file. And once the Abacus input file was exported, the optimization parameters for this particular beam sizing optimization or lattice sizing optimization was included, and then the Tosca solver, the Abacus Tosca solver, was called and was run, and the precursors for that particular solver was the two files that I just previously mentioned. And once the optimization results were complete, the optimization results were run through a Python script to convert it into a format that could be uploaded back onto the platform. So it's a pretty straightforward workflow, and the end result, and basically in this case, the optimization parameters, the beam sizing optimization parameters were chosen in such a way that I chose a range of beam diameters that I wanted to optimize it with. So I chose a beam diameter range from 200 microns to 800 microns, meaning thinner beams where loads are very minimal and thicker beams where loads are maximal. And I've kind of chosen this radius just to not go below the layer thickness of whatever you want to build your turbine blade with, because then you will have unnecessary fusion happening at really small regions, and this could cause much more greater problems than you just having a lattice. So that was one of the reasons why I'd chosen a much more higher diameter. As I said before, I ran the Python script to convert the optimization results to a supported format so I can bring it back onto the 3D experience platform. So this workflow is just once you hit go, it performs all the actions, and finally this is how your optimization result will look like. And the thicker beams near the dovetail region, or the regions of intersection between the blade and the dovetail, kind of indicated or rather correlated with what the simulation results that we saw before did, meaning there were some stresses on the higher side at that region, and we can see thicker beams as well over here. And once I brought in the lattice that was optimized, and after running the Python script into a format that was conducive, we can see that we have a completely integrated model of the new lattice, which has variable diameters, as you can see. So this indicates that we have thicker beams in the bottom, which correlates with whatever result that we saw in the previous frame. Okay, so this is my optimization piece, or this is my first phase of this entire workflow, which is complete. Now I want to take this to the second phase, where I want to plan my build around this particular geometry. So the build planning was done using an application called powder bed fabrication, which is by our sister brand Delmia. They are into virtual manufacturing. Basically, all the resources were selected manually for this case, and the blade was oriented at an angle of 45 degrees. We have an intelligent combination of primary and secondary supports. Primary supports are those kind of supports that are designed in CAD itself, so it comes in with as a proper CAD geometry. And secondary supports are those kind of supports that are generated in your pre-processing software. In this case, we used Delmia, or rather, in this case, we got the secondary supports generated in Delmia, and the primary supports were generated as CAD. So we have a combination of both, and these are some of the standard parameters that were used for this exercise. So as you can see, we have angle rotation between slices of 67, we have a laser power of 170, we have a thickness of 60 microns, the hatching distance is 140, and so on. So again, basic parameters that were used for scanning this. Virtual printing is the third phase of the workflow. So in this case, the optimized turbine blade was meshed with hex dominant elements, and as you can see, this is a cross section of the turbine blade itself. So it was meshed with a hex dominant element, as the name suggests. It's a majority of hex elements, and then it has the next one will be a 6-node element, the next one will be a 5-node, and the 4-node element as well. So this is the total element count. As you can see, we have about 3.3 million elements in this model, which is quite a size to perform some simulations on. And then the primary and secondary supports were also meshed using a combination of 4-noded, 6-noded, and 8-noded elements, as you can see from screen. And these are some of the statistics for the supports as well. So we have about 720 yards. So we have about close to about 4 million elements, excluding the build tray, to perform an additive manufacturing process simulation. And standard simulation parameters were used, meaning we had to ensure that the loads were properly transmitted from the build tray all the way to the top of the turbine blade. In this case, loads, meaning temperatures, because we are doing a thermal mechanical process simulation. So we are actually we are reusing the information that we previously created in the powder bed fabrication application. We're taking that scan path information and integrating it with our simulation over here, such that we compute the thermal profile at that particular moment, and then that will be used to drive the distortions and the residual stresses for the turbine blade itself. So to ensure that all the parts are connected, you want to have tie constraints between the parts, between the part and the build tray as well. We have initial temperatures, defining your chamber temperature as well as your relaxation temperature of the material, moving heat source, material deposition, and all of those features that will kind of like read in information that's coming in from the previous step, which is your Delmia part of bed fabrication, and then also give it some convective coefficients and radiation coefficients as well, so that appropriate cooling will happen amongst layers when it's building. So finally, the results, as you can see, we have a uniform stress distribution, implying that we have few stressor concentrations in the model. And again, this is just the first pass of the simulation. And we can see that there are some displacements that are higher near the shroud, meaning that we need better supports over there, or lack of better supports thereof, at least, because of which we can see some higher distortions. And that's about it for the actual workflow itself. So ideally, what I want to do taking this workflow forward is I want to test it with different lattice unit cell patterns and also with different beam sizes, different support structure strategies. I also want to check out with different scan path parameters to see how it affects it. And one of the most important things is to also introduce some cooling channels to the geometry itself, and to take this into an end-to-end process where I can remove it off the build plate, actually perform some heat treatment, and do some in-service on the new structure as well. So that's kind of like the future work of this particular project. But this project is to show, or rather focus on the workflow, that you can take a lattice and go all the way from designing a lattice all the way to production, as opposed to quantifying the results of what I've gotten here. So the focus is more on the workflow itself. And with that, I'd like to conclude my presentation, and I'll open the floor for any questions.